And I will tell you, you're in a good position because I don't know if you realize how your mind takes things in, but just to try to slow you down a little bit, I've boosted things up to between the 500 and 600.
Oh, cool.
So
Great.
so and you're still picking things up really quick. So
So
when you go onto your doctoral program, you're going to be just fine.
that's what I like to hear. That's I was kind of, I considered transferring because I was like, I don't want to like not that CSC doesn't have good things to offer. It's just like I want to be ahead. You know what I mean?
Oh, you're
So it
going to
makes
be.
me feel good.
Then if you decide to take some of those engineering physics classes, like the fluid mechanics,
That just sounds like fun.
it is once you get it.
Yeah.
Like I can tell you straight out, as you're studying math, start learning more about Bernoulli.
Bernoulli.
Bernoulli's going to be big in fluids.
Bernoulli. Definitely heard the name before. What level of math do you think I should get to if I want to take that class?
Differential equations.
Okay, easy. I can do that. Not even worried about it.
Because I mean, yeah, and Gregory will teach you everything. It's just the math in there is no joke.
Yeah.
It's also conceptually, fluids are not intuitive conceptually. I mean, we did a little bit of fluids last semester, but
Yeah.
we just kind of grazed the surface of it.
You don't have enough people that have math for that, I'm sure.
Well, it's kind of like, people, when you talk to people about blood pressure, and it's like, well, it has to do with the velocity of the blood through the system, because if you're talking about amount of blood, the pressure is actually less because you can only get to a certain depth within which is the radius of the blood vessel. And if the blood vessel constricts, that radius decreases. So according to depth, pressure is less.
Sure.
So it's like, but you register a higher blood pressure. Okay, well then it's not due to amount of blood. It's due to something else.
Yeah. It's like that thing you're talking about where like when it goes through like a tighter outfit, it goes faster.
It's just some of these things about fluids. It's fun if you enjoy figuring things out that are not intuitive. Like if it's not obvious what the answer is, then you'll enjoy fluids. Okay, so this is specific. Now we can use this equation for a lot of stuff. You'll find we can even use it for square planar complexes. It'll change a bit for tetrahedral complexes, but this is your basic crystal field stabilization energy. And so then, of course, you remember your delta zero is that energy splitting between the T2G and the EG level. And so you're trying to figure out exactly what kind of factor is that, what kind of factor of that split do you have? Is it more or less based off the complex? Because this will start to tell you about low spin versus high spin configurations. And then your ZP, we can take that apart a little bit. So your ZP really comes into play when you're looking at energy that's added between the low spin, high spin, and low spin. And it's really going to be this net change of electron spin pairs. Are they, if you have a D5 complex and you go from high spin to low spin, well, now all of a sudden electrons go from all being single electrons to pairing. And so what's that energy going to add to the system? And you find out that this pairing energy actually starts to become, and it's something to practice on because it's not going to be the most intuitive thing, but it's going to be a combination of this pi C, pi E. And this is just the way several textbooks represent it, so I went with it. But the capital pi in this case is going to be, so the sub C is Coulombic repulsion energy plus your pi sub E is quantum exchange energy. Now, one of the things to keep in mind is Coulombic repulsion energy sends orbitals way up in up in energy. Exchange energy is going to stabilize a configuration.
Okay. Wait, okay.
Because remember, the more electrons can exchange, the more they can delocalize, the lower the energy goes. I don't know if you would call that a true delocalization, but it's a similar idea.
Like induction kind of vibe,
yeah, it's like, well, these electrons are aligned like this, but this one could be here, this one here, and this one here, and this one here, and this. So all of your orbitals with exchange your orbitals are all start to blend into a single, like kind of like a single orbital.
Okay.
And it has a stabilizing effect.
Word.
You'll learn more about exchange energy when we do quantum chemistry.
Sounds good.
There's an entire quantum mathematical setup for it. And you'll see how you're going to actually, now in quantum chemistry, you're going to go through the math of actually pitting the Coulombic integral against the exchange integral and seeing how it affects the energy of the system.
Yeah.
Okay, so what we want to, yeah, I did. So what we want to do is like, let's just take an octahedral complex. Well,
Vanadium.
Well, we know that water is a neutral ligand. So that means this has to be vanadium-3. And when we go through and find out what its electron configuration is, we find out it is a D2 complex. Okay, so this one is automatically going to be a high spin situation. It doesn't matter what delta zero is. Or delta, oh, it's not a zero, it's delta, it's octahedral. So because they're always going to go low energy first. We only have 2 of them. This is just kind of how it's going to set itself up. Okay, so one of the you'll see terminology. It'll be represented as a T2G2 EG0. Let me make that EG bigger. It looks like it's EG0. So this is going to be its designation. When you look through articles and textbooks, you'll see a lot of these T2G3 EG1. I just want you to understand what the terminology means.
It's just referring to the number of electrons in each.
And it's a real simple thing to get, but if you've never seen it and you pick up an article and you're like, what the hell's a T2G2 EG0
Why is it square?
complex? Like what is this? What the hell's a T2G? Oh, well, that's the orbital symmetry. So many things that you hadn't seen before, you can now pick up an article and go, oh, I see what it's telling me. Okay. Now, let's look at the crystal field stabilization energy. So we're going to use that equation. So right there. So again, your N is going to be your number of electrons at the T2G and then your number of electrons at the EG. Okay, so we have a negative 0.4. Number of electrons at the T2G is 2 plus 0.6. There are 0 electrons at the EG level. Delta 0. This one is quite easy because there's zero pairing. There's 0 pairing. And so what we get is a negative 0.8 delta 0. So of course we can see this as a pretty stabilized energy. Now, when you take this apart, your P is going to have 0 Coulombic, but it will have exchange energy. So that's going to, the presence of the exchange energy is going to contribute to the stabilization of this. So it does have exchange energy. So you're going to find out that change in pairing is really going to come from your Coulombic term for the most part. It's something you have to practice with to get an idea of how it's really going to work. Okay, so now look at this. Why would this have exchange energy? What do you have to have exchange energy?
Like stabilization. So it's like, yeah.
You only have 2 electrons here. Trying to do something for those.
Can they pair and then unpair? Like,
It's not pairing.
not pairing.
So exchange energy occurs between two electrons that are not unidentifiable. It's two electrons you can't tell which one is which.
Oh,
Undistinguishable.
indistinguishable.
Indistinguishable.
Oh, okay. Okay.
So do you notice how these are two degenerate parallel spin electrons?
Yeah.
If you were just looking at them, you couldn't tell one from the other. So in quantum mechanics, that means that they can become each other.
Nice.
Welcome to quantum mechanics.
Cool. Come each.
You could almost make a comedy skit out of it. I'm me and you're you, but now I'm you and you're me. So am I still me, or is me or you, or is it? This is what they do.
That's really funny.
No, you're me and I'm you. Oh, okay. But what about if I want to be me and you want to be you? Well, I'm that also. It's just.
I like that. That's a good way. You should get started on that. If you ever get tired of teaching.
Oh, you could do a whole like who's on first skit with electron exchange. What about that guy over there? He's also us.
Yeah.
Is he us or is he him? Yes. But is he me? Yeah, but I thought he was us. He is. It's like, so quantum mechanics is fun. Now, some of these you're not really going to see a difference in pairing. Because like I could go to a D3 complex. It doesn't matter if it's high spin or low spin. D4 is where you're going to start to see some differences. Because then you either have an electron go up into the EG or pair with an electron in the T2G. So you'll start to see some real difference there. Let's kind of take that into account. Now, that's going to be kind of a middle field ligand. So that energy gap's still not insurmountable, but it's harder with the water. But let's look at a strong field ligand with the pi back bonding. Okay, well that whole ion's a negative force. What charge is on the iron?
2+.
2+. And when we look at that on the periodic table, that's going to the 2+ configuration is going to give us. So this is a D6 complex. Okay. Now, this is also a strong field ligand. Okay, so we can kind of look. So we know it's going to be low spin, but let's try to judge it both ways. Do you have your calculator with you?
I do.
Because I didn't actually calculate this. I was like, yeah, well, but like I know it's not going to be, but let's do a high spin configuration. Let's just look at this in terms of the delta zero. So if I did 1, 2, 3, 4, 5, 6, so then this would be your high spin configuration. And let's just say negative 0.4, and there are 4 in the T2G level, plus 0.6, and there's 2 in that level, delta Z, delta O. Okay, so what do you get here?
All right. I guess 1.6.
So negative 0.4 times 4 plus 0.6 times 2.
Okay, negative. Yeah. Yes. Yeah, negative 0.4.
Okay, so we're going to get a negative 0.4 delta 0. Okay. Or delta O. I keep calling it 0. It's not 0. It's O. It's octahedral. Okay, so then let's look at this. What is the pi C and the pi E? So there's one Coulombic term. Where does that come from?
The paired.
Yeah, so the paired. And then there's 4 pi E. Can you see those?
Yeah. Yes. Yep. All the ones on the same energy level.
Uh-huh. So there's one at the top, and then down at the bottom you can do 1, 2, you can do 3 different exchanges. Okay, now for your P for your high spin, you're going to add those together. Okay, now let's look at your low spin configuration. Should have given myself more room. But this one look like this. Okay, and so then your crystal field stabilization energy. There's 6 of those plus 0.6, 0 of those. Your change in your pairing energy. So this is going to give you a negative 2.4 delta O. So first off, you can already see a lot of stabilization with this. And then your ZP. Okay, so your ZP is going to become the difference in your pairing energies for between your low and your high. So what is my pairing for my low spin? I have 3 high C plus 6 for the exchange. Now, can you the three coulombs are easy to see. What about the 6 exchange?
Sure. So because you do 3 for all the up spins and 3 for all the down spins.
Yep.
Word.
Okay, so that means your PL minus pH. What we're gonna get. Okay, that's going to give a negative 2.4 delta 0 plus so so it's going to give us 2 Coulomb plus 2 exchange. Now this one is kind of easy to do. The others take some intuition. We can give myself a little more room. So negative 2.4, 0 plus 2. Plus 2p, that pairing energy. So the crystal field stabilization for the low spin is a negative 2.4 plus that 2p. 2.4 delta O plus that 2p. And you find that your low spin for this situation, especially with the strong field ligand, is going to be the more stable configuration. If only I'd given myself more room to write, but you know. And a lot of this stuff, it's going to start to make more sense as you go along. Okay, so let's show the crystal field stabilization energy for a low spin D5 configuration contains a 2p term, then explain the presence of this term.
So I'm gonna put all the spins on the T2G level, right? That, because that'll be the lowest spin.
Yes, yes. Because it's a D5. So remember, it helps to compare the high spin to the low spin.
And do I get 0 delta O? Am I crazy? Oh wait,
Delta O?
do I not need to do this CFSC? No, I do. What did I do wrong?
Well, your crystal field stabilization energy is going to be governed by your it's not really a difference between the two delta O's. It's going to be governed by the one that's dominant.
I just made in my high spin one, I got
Oh.
negative 1.2 plus 1.2. Is that like fine, or did I do something wrong?
Oh no, you didn't do something wrong. We're just not really worried about that term.
Oh, okay.
Now,
So just the P's.
but yeah, so you get a zero delta O. So when you actually take the difference, you're going to notice that you still have a
Negative -2 or whatever.
Yeah.
Okay, that's fine with me.
like the one we just did. If you did the full difference with the iron complex, you would end up with like a -2 delta O. But the crystal field stabilization energy of that specific iron complex is actually the -2.4 delta O. So you're not really worried about taking the difference between those two levels. At least to the delta O's, you're looking more the difference between the pairing terms.
Okay.
If you took the full difference, and that's for your crystal field stabilization energy. Taking the full difference will show you the full energy difference between both configurations. And you can see that if you get a stabilization from the low, like the high spin to the low spin, you're going to have a low spin dominance. So again, if we go back to the iron complex, we know that the crystal field stabilization energy takes on that 2.4 delta O as part of its crystal field stabilization. But if we did the full difference and we did the negative 2.4 minus a negative 0.4, we get a negative 2. So the difference between those two shows a stabilization of 2 delta O. So you look at it like that. Okay, so then we'll look at our high spin or low spin. Five. 1, 2, 3, 4, 5. Okay, this is going to be T2, G5, EG0. This one's going to have 2 Coulomb terms, 4 exchange terms. Okay, so let's look. Our crystal field stabilization energy for our low spin. And this will be a negative 2. Let's figure out that P term. Now, if we look at this, we can say, well, it's a little less intuitive because I don't have the full pi c plus pi e that I did. I could say, well, let's pull that 2 out front. That's going to give me pi c plus 0/2 pi e. But what we notice is that we are still going to get a 2p term. But it's all going to come from Coulombic interactions. The other way you can view this. So I did this step because you'll see this in different textbooks and whatnot. The other way you can view this. If I go from high spin to low spin, what's the difference in electron pairs?
2.
You can also do it that way.
Oh, okay.
But I don't want to just show you the easy way to do it and not talk about what is actually going on inside those terms.
Yeah, sure.
Because then you wouldn't know about Coulombic versus exchange interactions.
Right. Okay. But that's the easy way out.
Yeah. So, and what I was saying, like, let's say to talk about your crystal field exchange energy is going to be this one right here. Just like when we go back up, your crystal field exchange energy is going to be the negative 2.4 delta O plus 2p. Okay. Now, you can do a full difference where I take this term, I subtract this term, okay, and that would end up giving me a negative 2.0 delta O. You see that? Now, all that tells me is that as I go from high spin to low spin, I get a stabilization of 2 delta O.
Okay.
So then I know that tells me that the low spin is going to dominate because I get a stabilization of 2 delta O.
Right.
And so then from there, it's like, great. So it's going to be low spin. What's the crystal field stabilization energy? Well, that's where I go back to using the 2.4 delta O.
Okay, so total, but you can also take the
Right.
difference between them. Okay,
To see what your stabilization would be.
I see.
Now there will still be things, and this is just part of it, because remember you're caught in a like kind of an eternal tug of war, because this was a strong field ligand complex. Okay, what if I replaced all of these with chlorides?
It would be weak field. Right?
Weak field, and what's going to dominate your weak field?
The high spin.
High spin. So everything is at an eternal tug of war. And that's why in some of these areas, like in some of these areas of chemistry, you really have to pair the theoretical with the experimental.
Yeah.
Make your predictions theoretically, and then put these through the experimental paces and see what your results are.
Yes. And if the experiment doesn't add up, then your theory is wrong or something, or it's missing something.
That or something happened to the experiment, or the part of becoming a PhD is you learn to figure out what the difference is.
Yeah.
And sometimes those differences, the experiment's right and the theory's right, but there's still a difference.
Yeah.
And that's where you end up getting a Nobel Prize.
That's funny.
Because you figure out why is that difference there?
Yeah.
Well, that's how we found the matrices we're using in physics right now. That's how we discovered antimatter. Was I think it was Dirac was working through and was working out these matrices. Now this will mean more to you after you take quantum chemistry and you see the Fock matrices and stuff like that. But he was working these theories out, knew that a certain level of symmetry had to be maintained, and so he's like, great, I have proton matrices, electron matrices, neutron matrices. But no matter how many times I try, I can't get rid of these 3 matrices that are unknown.
Huh.
He's like, what are these? So I started doing experiments and oh, those are antiparticles.
Yeah, the evil twins.
Uh-huh.
Yeah.
So sometimes the theory's right and the experiment's right, and they don't agree.
Yeah, there's just something else.
So
that we
then
don't know
that
yet.
tells you there's something unknown.
Cool.
And that's where you go, oh, I'm going to figure out what that is.
Mm-hmm. Not spell that.
Okay, so Jahn-Teller distortions. So you notice we can get 2 of them. You have your original octahedral in the center. You can get an axial elongation or an axial compression. And this is all about symmetry breaking. So your radial distortions, you could now you can get axial compression. You could also get radial elongation, but you see that your D9 and D4 ions are often distorted. And what that does is you see these orbitals that are initially degenerate, and then the orbitals shift in a way that now they've broken the E and the T symmetry. So let's say you have a ligand system where there's more electron repulsion along the Z-axis. And it's due to the high electron density of the ligands, and that DZ orbital is going to experience more of that repulsion. You're going to get that axial elongation. So really, what the whole point is, it's these molecules will break symmetry, and their point group will go down in order to stabilize themselves. Sometimes you have ligands that don't allow, that just don't allow for some of the higher symmetry configurations. You can also get ligands where you have strong electron density repulsions and say you're dx squared minus y squared. And that's going to shoot that up in energy.
Okay.
So these are known as Jahn-Teller distortions.
Is that it's to become more stable?
Mm-hmm.
Is it like steric hindrance, or is it like?
The steric hindrance is more broken going from an octahedral to, say, a tetrahedral configuration.
Mm.
This is to alleviate electron repulsion.
Okay.
Yeah.
Sure. Okay.
I need to look it up. Part of me wants to say another textbook also said there had something to do with the magnetics due to electron spin. But I don't remember off the top of my head. But anyway, mostly you're like Jahn-Teller distortion, you're really trying to alleviate electron repulsion. Okay. Pretty sure I'm supposed to write something here, but I don't remember. Well, it's just that, again, your radial elongation, you can also get that. So we can get these. So that's where you're getting that electron repulsion within like your dx squared minus y squared. So you're removing breaking degeneracy. So symmetry breaking is going to alleviate that electronic repulsion. Tetrahedral systems. This one's a little harder to see. So let's try to. Oh, let's try to. Think about how some of these orbitals would fit in here. So I don't know, let's say, what if we did like our dx squared minus y squared? So we're going to get one that comes out this way. One that's there. One that's going to go back that way, and then one is going to come out that way. And then, so you see, the problem with the tetrahedrals, none of these orbitals are really going to hit head on. Okay. However, you try to say, well, if I treat each one of these locations as a point charge, how much interaction do I get? Well, for like this, so on the left here, I get a little bit of interaction from there and a little bit from there. On this one, I get a little bit from there, a little bit from there, so on and so forth. Wish I had given myself more room to draw these. Did I? No, I didn't. But if you go through and you start drawing all these out and you think about where does everything line up? Do a dx. These are so hard to draw. A dxz. Oh, I could do a YZ.
Oh, yeah. So it'll hit the two head on.
No, it's not hitting anything head on. Remember that one's way out in front.
So is this one like flat?
Yeah, so these two here are out in front, where that DXY is flat, and in the DXZ, that's the way this XYZ is set up. The DXZ there is like flat in the plane.
Okay, okay. So again, like the little half interaction.
Yeah. And so if you start drawing these in and you start trying to count it and you start counting up all those little half interactions, what you get is a d orbital splitting that is actually going to be the reverse of the octahedral complex. You know, you'll start to see you're getting more interaction by the dxy, dxz, dyz. And your dx squared minus y squared dz squared will stabilize. And now you notice that also these numbers have flipped. The 0.6 and the 0.4 have flipped. So now we have a new crystal field stabilization energy for the tetrahedral complex. Again, I wish I could draw these better, but I can't. I'm not good at it. Okay, so okay, so that now there's a relationship between your delta for your tetrahedral and your delta O. And that your delta tetrahedral is usually going to be about 4/9 of your delta O. Let's see. And so here, remember that this full split here, that's your delta O. And your full split here, that's your delta for your tetrahedral. Okay. You can also get your distorted tetrahedral systems with your strong, so your strong field ligands. So again, we're back to this idea of back bonding through pi back bonding. Also pay attention that your levels are now E and T2 instead of EG and T2G. We just want to make sure we stick with the symmetries of tetrahedral. And again, if you have a the tetrahedral complex has a highly degenerate electronic ground state, it may undergo Jahn-Teller distortion to relieve electronic repulsion.
Okay.
A couple of things. When you're calculating energies of a ligand field, if your delta for your tetrahedral is greater than your pairing energy, then distortion will occur and a low spin configuration will occur.
Okay.
So to predict the spin state, first off, you can get your delta O very simply taking our Planck equation, HC over lambda. And this lambda max, this is where your UV vis data starts to come in.
Nice.
And so you can start looking up data for the spectrochemical series, translate to your delta for your tetrahedral, compare to your P. Less than P, you'll get a high spin configuration. Greater than P, you'll get a low spin configuration. The low spin configuration for a tetrahedral is rare, may require 4D, 5D metals, where your pairing energy is lower.
Sure. So experimentally, we'd have a hard time getting delta tetrahedral.
Yeah,
Okay.
yeah. Now here's a question. You know how we've been talking about D4, D5, D6 complexes? Now I have 4D, 5D. What's the switch?
Which row we're in?
Yeah. So the 3D, 4D, 5D is just the rows of the transition metals. And then your D4, D5, D6, D7, D8. That's your electron configuration.
Okay, cool.
Other indicators of symmetry breaking and low spin, high pi acceptorability of ligands, and your 4D, 5D metals. So we'll talk about that more as we go along. But we're a little over time today. But I looked for so much information on these tetrahedral configurations, but there's just not a ton. This is the kind of thing that you need to get in the lab and start looking at your UV vis data and figure it out. But yeah, this is the best method that I could find once you start getting experimental data to try and figure out what your what everything's going to look like.
What is, okay.